So the second talk in the session is on improved conditional cube attacks on ASCON AEADs with a break-fix strategy, and this is authored as well as presented by Kai Hu.
Okay, thanks for the introduction. So this is about a new conditional cube attack on ASCON AEAD. ASCON AED has been selected as the winner of the NIST LWC competition. So its structure looks like this, and consists of 4 phases, including the initialization, which is the target of our paper. So for this target, the input is a 64-bit array, which was chosen and set as a fixed constant by the designers, and K0 and K1 are 128 unknown constants, and N0 and N1 are the nonces which we can control. For the output, we can omit the associated data phase and just access the encryption phase to use a P to get a C. Then we XOR them together to get the rate part of the output of the ASCON permutation. In this paper, we will consider the A-round ASCON permutation. ASCON AED has 3 variants called AES, ASCON 128, ASCON 128, and ASCON ATPQ. Our attack can be applied to all the 3 variants, but in this talk, I will only give the ASCON 128 as an example. So for one round ASCON permutation, it includes 3 operations. The first operation is PC, where 8 bits of constant will be XORed with the states. And the second operation is the PS, where 5-bit SBox will be applied to each column. And the PL is a 64-bit. So currently, the best distinguisher of ASCON initialization can cover 7 rounds, which is a cube distinguisher. In this distinguisher, we first set the N0 and N1 equal. Then under such a setting, we can find a lower algebraic degree. Actually, here they are the upper bound of the algebraic degree because we use some accurate method. In that paper, they use the 3 subset division property without unknown subset, but didn't counting the number of trials to calculate the upper bound of the algebraic degree. It should be accurate, but there is no theoretical guarantee. So for 7 rounds, the algebraic degree upper bound is ln 59. Here I write it as 66.5 because we can remove the last linear layer. So with this algebraic degree, we can use a 60-dimensional cube to get a 0 sum. However, at that time stage, there is no ideas how to use this cube distinguisher for key recovery attack. Why it is difficult? Let's say, because it's a cube distinguisher, so basically we have 2 ideas. The first is the cube attack, where we need to recover the superpoly of this cube. So for the superpoly recovery, there are also maybe 2 methods here. The first method is the division property. We need to find all the division trials to recover the exact superpoly, just like me said just now. However, because the ASCON's permutation round function is very, very complicated, so it's impossible to exhaust all the trials. So this method cannot be applied here. The second method is the borderline cube, which was used by the designers to give cube attacks up to 6 rounds of ASCON initialization. However, here in the borderline cube technique, the cube variables should be set in a specific set, and then the superpoly will only involve a part of the superpoly, a part of the keys. So a theoretical method can be used to construct the superpoly. But because for the best cube distinguisher here, we need to set N0 and N1 equal, so we do not satisfy that special structure. So superpoly recovery with the boundary cube cannot be used here, neither. The second idea is the conditional cube attack, where the output degree will leak the key information. However, if we use the traditional way for the conditional cube attack, it's also impossible. here because it seems we should cancel the 59 degree term, the max degree term. It's almost impossible. Why? Let's say the traditional ways. For R+1 rounds, we need a cube structure with two R variables. Then after the first round, the degree of the state should be still 1 because the cube variables will be set in specific positions to make the first round be a linear function. However, after the second round, then there will be some 2-degree terms. Let's say all these 2-degree terms related to x1. Usually they will be also k-related coefficient of the 2-degree terms related to x1. So if all the coefficients of such terms are all 0, that means x1 and xi, such terms will not appear after the second round. And also after the R+1 rounds, the max degree term will also not appear because the degree of the round function is 2. But if some coefficients is not 0, then that means some x1 times xi will appear. That will also that will lead to the max degree term. But it is based on assumption that such term will really appear. However, in our case, it's much more complicated because in our case the max degree is 59. The 59 degree terms can be obtained by adding the 30 degree term plus the 29 degree term or the 31 degree term and the 28 degree terms. So it's much more complicated. So we need to introduce some new strategy for the conditional cube attack. In our paper, we call it a break fix. So it has 2 phases called a break phase and a fix phase. Okay, so such a new strategy is based on such an observation that the very good, the lower algebraic degree is based on a very fragile structure that we need the first nonce and the second nonce be equal. So we can introduce a new cube structure where we introduce a disturbance here. So for the first position, we let the first cube bit, first nonce bit here is x0 plus 1. And in the second is x0. And for other positions, they are still equal. So we introduce a slat break here. So after breaking it with the same method, 3-subset division property, we can check the algebraic degree upper bound. After the breaking, it increases. So for example, for the 7th round, it's increased from 59 to 60 now. Okay, so we manually create some conditions here, actually. So the next phase is the fixed phase. So to do this phase, we should know what has changed. So we draw the algebraic degree after the first S-box layer. We will find that in the 3rd row, a bit becomes 1 degree from the 0 degree. So it changed. The NF of this bit looks like this. However, there is no k coefficient before the Olen 1 degree term. So we cannot have the k conditions after the first S-box layer. So let's say the second S-box layer. So for the second, after the second S-box layer, 3 bits become 2 degree from the 1 degree. So the NF of the 3 degree looks like this. So there are 8 2-degree terms here, and every 2-degree terms has its coefficients. So we can control the k efficiency to influence the output cube sum. So if these 2-degree terms are all cancelled, will the degree go back? And our answer is yes. So because the ASCON round function is designed with the cross style, so with the very simple calculation, we can calculate the degree upper bound for several rounds. So after the calculation, we can find after the fix, because we start from the second layer to set the algebraic degree. of the states, and then use the two formula here to calculate the upper bound of the after 7 rounds, and we determine that it algebraic degree upper bound running goes down again. Okay, so next is some details of how to cancel these 2 degree terms. Firstly, because we will use a 60-dimensional cube as the cube test term, so we have 4 free cube variables for us to control. We can set them as 0. For example, here we can set the V3, V25, V1, and V4 as 0. So these 4 2-degree terms will be cancelled. And the remaining 4 2-degree terms can be influenced by the k coefficients values. So if the k conditions hold, the 4 k coefficients are all 0, then the algebraic degree will go back to 59. Otherwise, the degree will stay 60. This has been checked by the algebraic degree matrix method, and we assume it's a tight bound. So the whole process is like this. So firstly, we zero 4 cube variables, and then we compute the cube sum. If the cube sum is 0, then we know that the 4 corresponding k coefficients are 0. Otherwise, at least one of them are non-zero. And for the 8 k coefficients, once we find 4 0 k coefficients, then we can recover all the 8 k coefficients, because we can combine the 3 0 1s with the unknown ones, and then do the cube tester. If the cube tester is 0, we know the final one is 0. If it is non-zero, we know the final one is 1, because if 4 are 0, the cube sum will definitely be 0. That is also to say we need a trigger for k for the 8 k coefficients. We call such a k coefficient 8 k coefficients related to initial structure k set, and if it has a trigger, then we call it a good k set. The whole algorithm is like this. So for each initial structure, we choose 4 cube variables, 4 corresponding cube variables, and set them as 0. Then we do the cube test to observe the cube sum. If the cube sum is 0, then the 4k, then we know the corresponding 4k's are 0, and put them into a set k. Otherwise, we put the 4k's into another set n. And for all the 4 tuple in the n set, if then we check the coefficients in the k to see if there are already 3 of them are 0. If so, then the remaining must be 1. We can remove it from n. And finally, the k coefficients in the n set will be calculated by the exhaustive search. So the whole complexity consists of 2 parts. The first part is the algorithm, is the complexity from the algorithm. The second part is the exhaustive search after the algorithm. Of course, we want the exhaustive search complexity should be less than 272, because the first part complexity has been there. We cannot cancel, or we cannot reduce them. So we do not want the exhaustive search becomes the dominant part. To avoid it becomes from becoming the dominant part, we need to recover at least 58 bit from above algorithm. So we need to calculate the probability, and also to know how many k's can satisfy our condition. So firstly, we need to know how many good k sets are expected for a random k. A good k set appears with the probability 0.63, because the expectation can be calculated without the independence requirement. But because all the k sets are not independent, so we cannot. We find that a normal distribution does not work well here. So we use a new distribution called a school normal distribution. So you can say it's very like a normal distribution, but it has a school. Okay, so to recover 58 independent k coefficients by the experiments, we find we need at least 20 good k sets, or with the probability 0.991. Here, we stress independent because for 2 different k sets will contain some common coefficients. So here we use experiments to calculate how many good key sets we need. And according to the school normal distribution, we find the probability that a random K can have at least 20 good key sets. The probability is 0.986. That is also to say the K space size which we can use which we can recover with the complexity without the exhaustive search being the dominant part is 2 to 127.97. Okay, the whole complexity is like this. So for this case, we can recover the case with that algorithm and the exhaustive search. So the total complexity is about 2 to 72 still. And for remaining case, because there are no many good key sets, so we cannot accumulate 58 key coefficients. So the complexity can increase a bit. For simplicity, we just directly consider the worst case where there is no good case sets here. So by experiments, we find among 2 to 23 cases, there are 420 ones that have no good key sets. For this case, the size of this case is about 2 to 104.7 case. So we just do the exhaustive search for this case. This is the worst case. And for data complexity, because for each initial structure, the attack will cost at most 2 to 64 nonces. So for the whole attack, it will cost 2 to 70 chosen nonces. Next are the weak key attack introduced in our paper. Why we want to consider the weak key attack? Because from the designers, they set a limitation to the ASCON AAD that 1K can protect at most 2 to 64 blocks. So we already break the limitation. So we introduce the key coefficients. Here it's very simple. You just assume that 3 key coefficients are known, then you can recover other key coefficients with a similar philosophy. Okay, so these are the results. And also our attack based on assumption, we do some experiments. However, for 5 round, it failed completely. For 6 round, about a half can succeed. But for 7 round, I think there is a trend that for more rounds it will be successful. The case will be much better. So let's do a simple comparison between the two strategies for the traditional cube attack. So for the canceling strategy, traditional one, so as the assumption is more reliable because other 2-degree terms are already prepared here. But the negative is usually it only applicable to 2R size of cubes. However, for our strategy, it's easier for non-2R cubes. That means we can firstly try our best to find the best cube distinguishers. Then we introduce the disturbance to break it, and finally to fix it by introducing some key conditions. But the negative is the assumption is more fragile because actually we expect only one 2-degree term will bring the max degree term. Okay, thank you. Sorry.
Thanks a lot for the presentation. Do we have a quick question? We do.
So can you go to the wiki part?
Yes.
So you use the wiki here to stay within the 2 to the 64 requirement, right?
Yes.
But does this include the probability of the wiki, or you're already assuming that the key is weak and then?
Yes, but I think the weak key condition means the complexity of what you use should be do not consider the key information you have known, right? So
Nope.
So if the weak key attack can still better than the exhaustive search, so it should be a valid key recovery.
Yeah, so is the wiki probability here like high enough that it will not impact the attack so much?
Yes. Yeah.
Any additional questions? Maybe just a very brief one from my side. So you mainly focused on the case of AES 128. So are there any differences for 128A, or is it pretty
In my
much the same?
attack, it seems no difference for 128, but for ASCON ATPQ, we first need to recover the 32 bits of key in the first row. That can be done very easily with our strategy or with the previous strategy. And that complexity is small, is not the dominant part. So after you recover the constant, the keys in that part, the other attacker is still the same with this.
Okay, thanks. Well, then let's thank both speakers of the session again.